A 3-meter long pole has a 5 kilogram basket of tomatoes on one end and a 75 kilogram counterweight on the opposite end. The pole itself is placed on a pivot, and the pivot is half a meter away from the counterweight. Initially, the pole is horizontal and stationary, but the weights are released, and when they are released, gravity will pull the counterweight downward, and the pole rapidly begins to spin about the pivot. And we are asked, how fast is the basket of tomatoes moving when the pole makes an angle of 45 degrees with the horizontal? So essentially, we want to know how fast are the tomatoes moving right here if initially everything is stationary. To begin answering that question, we will ask how high up vertically did the basket tomatoes rise and how high vertically did the counterweight descend. So we are essentially asking, what is this height going to be and what is this height going to be? Well, to answer these questions, this is just going to be some basic trigonometry. We know that the pivot is 2.5 meters away from the basket of tomatoes, so I could draw a right triangle. The hypotenuse will be 2.5 meters, and if this angle is 45 degrees, I could use trigonometry to determine that this vertical height will be 1.77 meters. Similarly, if I were to draw a right triangle with a hypotenuse of 0.5 and a 45-degree angle again, we would essentially find that the vertical height of this triangle is going to be 0.35 meters. So I could say the basket of tomatoes have risen 1.77 meters into the air. The counterweight has descended 0.35 meters. So we'll draw this in. Here's 1.77 meters, and here's 0.35 meters. Now let us find the force of gravity on these objects. The basket of tomatoes has a mass of 5 kilograms, so I could say the force of gravity on the tomatoes is going to be m times g, 5 times 9.8. That will be 49 newtons. The force of gravity on the counterweight will be 75 times 9.8. That's 735 newtons. So I drew in the force of gravity on the tomatoes is 49 newtons downward, and the force of gravity on the counterweight is 735 newtons downward. Ultimately, what we want is the speed of the tomatoes at this moment. So how could we find speed? Well, speed v is related to angular velocity. So if we could find the angular velocity at which this device is spinning at this moment, then we could use the relationship between linear velocity and angular velocity to find the speed of the tomatoes, which is what we're after. So finding omega will help me find v. We could then ask, well, how do we find omega? Knowing the kinetic energy at this moment will give me omega. Even though I have two things that are moving, we're assuming that the rod has a very low mass and the only significant masses are the tomatoes and the counterweight. If I know the rate of rotation of this device, well, then I could find v. And if I know the kinetic energy of the device entirely, that will give me the rate of rotation. Because the angular velocity, the number of radians per second that the tomatoes are moving at, must be the same as the angular velocity of the counterweight since they are connected. So finding the kinetic energy of rotation will give me omega, which gives me my speed. How do we find the kinetic energy of rotation? Well, we notice that at this moment, the device is not moving, and at this moment, it is moving. There was a change in kinetic energy. To find the kinetic energy of rotation at this moment, we're going to look for the total work done on these objects. Here, the force of gravity will be the force that does work on the objects. And then we'll use the work kinetic energy theorem to find kinetic energy of rotation, which will give me omega, which will give me v. So this is our game plan. The first thing we want to do is to find the work done by gravity on these objects. So how can we do that? Let's first consider the work done by gravity on the counterweight. So I'll draw that out. Here is the initial moment when the counterweight is horizontal, but then gravity takes over, pulls the counterweight downward, and some amount of time later, the counterweight is over here. I could say the counterweight went through some displacement. Displacement is the vector pointing from the initial location to the final location of the object. Here's my displacement vector d. We also said that the displacement of the counterweight in the vertical direction is 0.35 meters. In other words, the counterweight descends vertically 0.35 meters. So I'm going to draw that in. Here is the 0.35 meters that the counterweight descends. Throughout this motion, the force of gravity is straight down towards the center of the Earth. So I could draw the force of gravity vector looking something like this. Here's the force of gravity. And when we learned about work back in chapter 6, we learned that the work due to a single force is given by the equation W equals Fd cosine theta. In this equation, F is the strength of the force pushing or pulling on an object. D is the displacement, the distance that the object travels. And theta is the angle between the direction of the force vector and the direction of the displacement vector. Now, if you wanted, you could use trigonometry to determine the total displacement, because you know this and this length are each 0.5 meters from the picture here. You know this angle is going to be 45 degrees, so you have enough information to find all the terms in this equation for work. However, there's a more elegant way we could think about this. Let's think about what the terms in this equation for work mean. F is the strength of the force, as I said. D is the displacement. And I could think, if I want, of this term cosine theta. This is a term that projects one vector onto another vector. So let's think about, what does it mean to project something onto something else? Let's say we have two vectors. Here is vector A. I'm just being completely arbitrary with what type of vectors I'm talking about. And here is vector B. Now, if I say what is the projection of vector B onto vector A, essentially I'm asking, if I have a really bright light and hold it way up here and shine it down on vector B, how much of vector B's shadow will lie on vector A? So I will draw a line that is perpendicular to vector A and goes right through the tip of vector B. And if I look, well, here's the angle between vector A and vector B. This is angle theta. And this right here, this is going to be B cosine theta. So let's see what we have here. This segment right here, B cosine theta, this segment will be at most equal to B. When this segment is equal to B, the magnitude of vector B, then that would be like saying vector A and vector B are parallel with each other. When this segment is equal to 0, that is saying like B is going to be perpendicular to A. In this case, B is not completely perpendicular to A and not completely parallel to A. It's something in between. This cosine theta term ensures or accounts for the fact that these two vectors somewhat align but not completely. Without loss of generality, I could imagine vector A being projected onto vector B. I'm going to keep these same vectors here. I'll just erase this and that. And I could imagine, what if I wanted to just extend the direction of vector B? So here I drew a thin dotted line extending the direction of vector B, in a way continuing it on a bit, even though vector B only has this much magnitude. And I could ask, if I were to go way down here and shine a light shining up on vector A, how much of vector A's shadow would fall on this line here that is aligned with the direction of vector B? So I could say here is a perpendicular to vector B, and I would say the extent that vector A projects onto vector B is going to be, again, this amount right here, which is a cosine theta. The thing to take away from this side discussion that I'm going on is the cosine theta term is a term we could imagine projects one vector onto the other vector. Now, specifically for this example here, we could imagine that this cosine theta will cause the displacement vector to be projected onto the force of gravity vector. So I could say that the term d cosine theta in here is going to be equal to 0.35. The vertical displacement, 0.35 downward, is the projection of the displacement vector onto the force of gravity vector. The projection of d onto f is d cosine theta, which is 0.35. Now, because the displacement is overall in the same direction as the force of gravity, I expect that to be positive work done. So I could write the work done by the force of gravity on the counterweight is going to be W equals 735 times 0.35, and I get that is equal to 260 joules. By a similar line of reasoning, I could look at the work done by gravity on the tomatoes. So if I want, I could draw the same picture out. If I were to draw the initial and final orientation of the tomatoes, initially the rod is horizontal with the tomatoes on the end, but then later on the rod is at that 45-degree angle. Therefore, I could say this is the displacement vector for the initial to the final position of the tomatoes. The tomatoes in total have risen a height of 1.77 meters. We calculated that out at the beginning of this problem. And the force of gravity on the tomatoes is straight down with a strength of 49 newtons. So the force of gravity is always going to be straight down. Here is the force of gravity on the tomatoes. And the vertical component of the displacement is 1.77 meters, as we said. So the vertical part of the displacement, 1.77 meters. We could say work done by gravity on the tomatoes as FD cosine theta. And again, I am thinking of this 1.77 upward as being the projection of D onto the force of gravity. Now, because these vectors are overall pointing in opposite directions, not completely opposite, but more opposite than not, I am expecting that the work done by gravity should be a negative number. So I could, in a way, think of a projection of one vector onto another vector. So if I ask how much is this vector projected onto this vector, well, if I were to shine a really bright light straight down and the shadow would be cast and be something like this, because this vector is overall pointing in the opposite direction, I guess I could kind of think of that as a negative shadow or negative projection, however you want to think about it. So I could imagine that would cause this term to acquire a negative sign. Regardless, I still see that the force of gravity and the displacement are pointing in different directions as opposed to the same direction, so I expect work to be a negative number. So work will be negative 49 times d cos theta, which is 1.77, which is negative 86.6 joules. Now, to find the total work or the net work done, I add the work done by gravity on the counterweight to the work done by gravity on the tomatoes. So this is the work done by gravity on the tomatoes. We found the work done by gravity on the counterweight to be 260. So I could say W net is equal to 260 plus negative 86.6, which gives me a total work done by gravity of 173.6 joules. Now, before I go on to continuing to solve this problem, there's two comments I'd like to make. Number one, we had an interesting approach to solving this problem, but we have done something like this previously in this course. Back when we were learning about work in Chapter 6, we had an example problem where there was a ball that was rolling off a table, and the ball then goes and falls to the floor. So what we did is we said, here is the initial location of the ball, here is the final location of the ball. So this is the ball's displacement vector D. We also said that we know the table has a height of 0.8 meters, so here's a height of 0.8. When we calculated the work done by gravity on the ball, we said, okay, work is equal to FD cosine theta, and even though we do not know the angle at which this displacement vector is oriented, we don't know the magnitude of the displacement vector, we know that this 0.8 term must be d cosine theta. So rather than thinking of this equation for work as we must have a number to plug in everywhere, we said we have one number and we could plug this one number in for these terms here. And then we did it and proceeded with the problem. What we have done here is essentially the same thing that we have done in a previous example problem. The second comment I would like to make is that you might say, well, wait a minute, isn't there another force acting on the tomatoes and the counterweight? The tomatoes and the counterweight are moving in a circular path, so shouldn't there be some force that is responsible for their radial acceleration? There should be one force pulling them inward. Presumably the bar is pulling them inward, and that will cause them to move in a circular motion. It is true, there will be a force from the bar that keeps the tomatoes and the counterweight moving in a circular path. So why didn't we account for this force when we were calculating the work done? The reason for that is this force will not do any work on the tomatoes or the counterweight. To see that, let's imagine, instead of thinking about the initial moment to the final moment of the tomatoes, let's just think about a small increment of motion. When the tomatoes are right here, and then when the tomatoes have moved ever so slightly more, so just a little bit more, throughout this motion, I would say the displacement vector is going to be pointed in this direction. However, the direction of the force, the force that keeps it moving in a circular motion, is going to be inward towards the center. The direction of the displacement vector, which is going to be in the same direction as the velocity vector, will be in the tangential direction. The direction of the force vector is going to be in the radial direction, inward. These vectors are always going to be perpendicular. So when I calculate the work done by this force, I'll get cosine of 90 degrees, and that will be zero work done. Finally, I will say that if you did not like how we calculated the work here, you can always use trigonometry and just say, we know the initial and final positions of the tomatoes, so we could just calculate the displacement vector in its entirety. We know the force of gravity is straight downward, so these vectors are going to be offset by 135 degrees. And then you could go for the traditional work equals FD cosine theta with a number plugged in for theta, for F, and for D, and you end up getting the same result as what we got right here. So now that we know the total work done on the objects, we essentially know what the change in kinetic energy was of this contraption. We could say the change in kinetic energy is equal to the work done by the work kinetic energy theorem. And so I could say change in kinetic energy was 173.6. The initial kinetic energy was 0 because nothing was moving. So I could write that as final kinetic energy is 173.6. So 1/2 I omega final squared is equal to 173.6. Before I find omega final, I first need to determine the moment of inertia of the system. We are assuming that compared to the mass of the counterweight and the tomatoes, the rod is very light. That is essentially the same thing as saying the rod has practically 0 moment of inertia. So the moment of inertia is going to be the moment of inertia of the tomatoes plus the moment of inertia of the counterweight, which we're going to approximate as point particles. So I could write the moment of inertia of the system as being mr squared for the tomatoes plus mr squared for the counterweight. So the mass of the tomatoes is 5, and the tomatoes lie at a distance 2.5 meter from the center of rotation. So I get my 2.5 squared. Plus the mass of the counterweight is 75, and the counterweight is a distance 0.5 meter away from the center of rotation. When I put these numbers in a calculator, I get the moment of inertia for the system is 50 kilogram meters squared. Now I could plug numbers in and find the final angular velocity of the system. When I do that, I get 173.6 equals 1/2 times 50 times omega final squared. From this, I find the final angular velocity of the spinning object is omega final equals 2.63 radians per second. Now we want to find the final speed of the tomatoes, the speed of the tomatoes at this moment. The tomatoes are moving in a circular path, and we know their angular velocity, so we could find their linear speed. We have v equals r omega, so the speed of the tomatoes is equal to the distance that the tomatoes are from the center of rotation. That is r in this equation. In this problem, the tomatoes are 2.5 meters away from the center of rotation, so I have 2.5 times the angular velocity of the tomatoes, 2.63 radians per second, and I find the speed of the tomatoes to be 6.575 meters per second.